Welcome to Terra Talks, where we talk about all things real estate. In each episode, we'll tackle current trends and topics of interest, both locally and regionally. However or wherever you decide to tune in, you're not going to want to miss this.
Welcome to Terra Talks. My name is Brian Puckerin. Today our guest is Mr. Greg Parris from Consulting Engineering Partnerships, known as CEP for most people. Welcome, Greg.
Thank you, Brian.
How are you doing?
I'm doing great.
Okay.
Yeah.
So Greg is a civil engineer, 25 years experience.
Yes.
Can you tell us what a civil engineer does?
Yeah. So I would say I'm a civil and structural engineer. The reason they say that is that, as you're aware, Brian, most students that do civil engineering, that's what they do as a base course.
Yeah.
So picture that if you do mathematics, math has trigonometry, statistics, it has algebra. So civil engineering has several disciplines. You have structural engineering, coastal engineering, environmental engineering. So we learn all of these topics, but after one can specialize. So for me personally, I would have specialized in structural engineering.
Okay.
So yes, I have a degree in civil engineering, but a master's in structural engineering.
Okay.
So structures are
Your
what
thing.
I love. I would say my first love in terms of the profession.
Okay.
Yeah.
And what does a structural engineer do?
Well, I can still answer your first question. I forgot that first question. But again, the structure. So civil engineering really deals with the infrastructure, the built environment.
Okay.
So when you drive on the road, the lane width, the drainage infrastructure on the road, where you have stopping signals, traffic signals, that's all designed by highway engineers, which is part of a civil engineering course. In terms of, if you look around again, bridges, bridge engineering is also a unique aspect of civil engineering. We could go into environmental engineering as well as geotechnical engineering. Geotechnical is what it says it is. It really deals with the soil, investigating the soil to see if the soil can handle the loads from a structure. Now into structures. Structural engineering deals with making a building stand up, in layman terms, making the building strong. Most people, when they want to do a project, they would firstly approach an architect.
Right.
That architect discusses with the client the vision that they would have. They would talk about things like how many rooms, what type of rooms, the use of the building, space requirements. And sometimes, not everyone wants a very standard project. People want to stand out. And as structural engineers, that's where the challenge comes, where we have to make sure that, given the design, what can we do to make sure that the building is structurally viable, is safe, and we deal with making sure that the structural elements along the load path,
Right.
from top to bottom, are strong enough to take those loads.
Okay. Who would use your services and what would they get from you in terms of documentation, explanation, things like that?
Yeah. So clients can vary tremendously from homeowners, developers, bankers, real estate agents, homeowner in the sense that, so nowadays a lot of homeowners are becoming more conscious of that hurricane threat. Before there was apathy, Barbados, we are spared, that sort of discussion.
Yeah.
But now we find that more homeowners now are saying, look, we want to get an engineer involved. So that's where we would come in. People also like to purchase existing property.
Correct.
And they would want to know that what they're buying is structurally sound. So they request a report from an engineer, structural engineer. You have the developers. Obviously, development is a large plant. So therefore, a developer will want to ensure that their investment is well secured, and that it's safe. Bankers or lenders, again, it comes back to money. Money. Bankers as well, they want to make sure that their investment is secured. Okay. So sometimes they would have, if someone is purchasing a property or house, they want to make sure that when they lend this money, that this thing don't collapse or their defects within 2 years of lending the money to purchase the property. And obviously real estate agents, because your job entails inviting clients or prospective buyers to look at property, and sometimes they may see a crack or a defect.
Yeah.
And then you may advise them, look, have an engineer look at it.
Yeah.
To advise if it's a structural crack or just cosmetic.
Yeah.
Right? So that would be the level of clients you will have. Obviously, government, because we must understand that the Barbados Engineers Registration Act states once it is a place of public gathering, an engineer must be involved. If you're doing a church, a mall, office building, town hall, any place that is a public gathering, the laws of Barbados state, you must have a structural engineer, an engineer involved, right? And that's where you start getting into the differentiation between a residence, two-story residence, single-story residence, where you may not need an engineer.
Right.
But then we start getting in now more to complex structures and places of public gathering, the law requires it.
Okay. Barbados National Building Code. Tell us a little bit about it. Who should use it, when it should be used, and if it's being used.
Barbados National Building Code first came about in 1993. So there's a Caribbean Uniform Building Code that was original code.
Okay.
And that code looked at loading, looked at hurricanes and earthquakes. But then what you may have a situation where there's spin-off standards or guidelines. Mm-hmm. In 1993, we had a Barbados Building Code that was more prescriptive. What does that mean? That means that if you are a homeowner and you're building a slab, you can look in the document and see what you're supposed to be witnessing on site. Mm-hmm. So that would be more prescriptive. I'm telling you how to build a slab. In 2013, it was revised. Coincidentally or ironically, the revision was not as prescriptive. Why? I believe that it was a situation where you don't want a person building their property to believe that one plaster fits every store. That happens. Right. What does that mean? You can have a person that has built a house. They have used a certain size wall, thickness of wall. Mm-hmm. They're doing another structure with larger spans, and they're using the same thickness of wall or same depth of beam, size of column. Mm-hmm. And it sort of tried to safeguard against that type of person that would try to just look at the standard and apply every detail to every building. Right. So it's not as prescriptive. It's it's a lot of words, very little diagrams. Our codes are not enacted by law. And as a result, you have a situation, unlike other Caribbean jurisdictions, and because they get hit more frequently by hurricanes, they're more serious. In fact, in 1995, when Hurricane Louise hit St. Martin, mm-hmm. that was a wake-up call to the region to take building codes more seriously. As you are aware, St. Martin is Dutch and French.
Correct.
The Dutch side enacted their laws, building codes, and did a lot of enforcement. The French side were not as driven to do that. When we had Hurricane Irma in 2017, yes, there was severe damage on both sides, but the Dutch side was more resilient. They were able to recover faster mm-hmm. because their structures were more built to a standard, whereas the French side took longer to get back on their feet. So it shows that the importance of building codes. As again, in Barbados, we are not regulated. The code is not enacted by law, and therefore you could have a situation where, Brian, you're building your house next to me, and building my house, two different contractors, and they're doing two different things for the same type of design. Because these guys, they may be building based on experience. We did this 10, 20 right. years ago, house didn't fall down, I'm going to continue to use it. But Barbados, we haven't experienced anything of any major magnitude. I was in Grenada in Ivan 2004. I went to Barbuda, Irma 2017. And trust me, the Beryl's and the Elsas and the Thomases in 2010, I want it to remain don't go past that level of event, because these forces are extremely strong. In fact, the pressure is proportional to the square of the wind speed. Mm-hmm. All right? So that's mm-hmm. important. So it's not just a linear relationship. The pressure is proportional to the square of the wind speed. So damage can be very, very significant. In fact, on average, GDP for Category 4 repair is like 200%, 150% of GDP. Right? Grenada would have experienced that. Okay? So our building code is not an enacted document or mandated by law. After ELSA in 2021, I know that a lot of work was done on formulating a document that has been prepared, but it has not been enacted or passed as a document as yet. That document that I would have seen would have given, in terms of house construction especially, more quality control in terms of engineers having to go out and check to make sure that they're being built to a standard. And we must remember what building code is. A building code is like a rule book for safe construction.
Right.
In other words, a building code is also can be considered to be a minimum accepted standard. In other words, if you're doing something, your standard should not be less than this.
Okay.
So it's basically telling someone how they should be building. Obviously, when you get into more unique structures, you have to now involve an engineer to help with the structural component to make sure that it's still stable.
Okay. That's a lot. And
Yeah.
I'm not sure I knew all of that. I thought that we were required by law, or to some extent, to use the building code.
There was an event back in the 1990s where a British visitor, and I'll show you how the law can work. She had booked a vacation to Barbados through her booking agency. And she was staying at a hotel, and she had walked through the glass and got severe cuts. And she sued the booking agency. And their argument, I believe at the time, was, but we don't have any standard building code. But the 1993 edition had said the glass should be of a certain type in that use. And her lawyers argued that point. He said, yes, even though it's not a mandated document that should be, that is a regulatory document enacted by law, it exists as a minimum standard.
Right.
And therefore, it should have been used. And she was successful. She won the case. So it shows that even though it's not a document that is mandated by law, it was still used as that the country has a standard, and it was still used to argue a point. And they won.
Okay.
Yeah.
I see you have some models. I'm a little bit excited about models. Tell us about the models.
Yeah. I'm going to focus on the first two. And the first two, we have a single-story building. Let's call it a house. Let's say this is a house. If those on the camera can see, and I will describe it for those listening, we have a model here where we have some cables or forming the shape of an X. In engineering, we call it cross-bracing. Most of you would see this type of arrangement if you go into like any warehouse building or supermarket, where if you look in a supermarket at the ends of the building, along the edges or sides, you will see these cables forming the pattern of an X, in most cases. These are similar to what we refer to as a shear wall. I don't want to make you get scared now because you hear shear wall. And shear doesn't mean that we're sharing loads. No. Shear is SHEAR. And what that does, a shear wall, helps to resist lateral forces. Because as engineers, our most difficult loads to get to the ground are not the gravity loads, we're load-bearing walls. So load-bearing wall and a shear wall is different in their definition. A load-bearing wall takes gravity loads from furniture, people, objects. A shear wall helps to resist lateral forces. What are lateral forces that we experience every day? Hurricanes, earthquakes, mudslides, pushing on the building. Those are the hardest loads to get to the ground. Gravity loads just through the beam, to the column, to the foundation, straightforward. So these cross braces are analogous to shear wall.
Okay.
Where it gives a very stiff type of response. So that's why you would see in like the Barbados Building Code 1993 and even the OECS Building Code Building Guideline, they have specifications where you want a solid wall at specific portions of the house from foundation to eave.
Right.
Solid, no window openings, nor door openings. So case in point, our 1993 edition, I have to reference this because it's the most straightforward one to understand and to explain. It states, on each elevation of a house, you must have at least 3 meters, one panel, uninterrupted from foundation to eave, that's 10 feet, or 2 2-meter panels, uninterrupted from foundation to roof. Obviously, if you do not have this, the building now struggles from a lateral perspective, and that's where engineer will need to come in again and try to use whatever the architect is showing as strong points to make the building stable.
Okay.
So if we had Hurricane Brian can come along and Hurricane Brian said, I'm a category 4, and Hurricane Brian start to shake this building, I don't expect to see any lateral movement because I have all of my braces around the building. So these represent shear walls, all right? If it starts shaking, it's not budging. You can see it's very, very stiff.
Yeah.
That's what walls do as well. Walls make a building very stiff, right? So we use walls as strong points in the building to help resist this shaking effect. It's not going to go anywhere. House number 2 is a house that we see so often in Barbados where a homeowner may have financing to do phase 1. So they have the house done, 2-story house, drawn up, phase 1 and phase 2. The lending institution would say, do the upper portion first, because the roof will be completed in that upper portion as opposed to doing the lower portion that will have a concrete slab as the roof. And then you come back a few years later and finish up the building. So lending institutions would always look to say, do the top story first and fill in the bottom story after. So often, this bottom story is constructed from concrete block piers. On occasion, clients may or homeowners may use reinforced concrete. And you have a situation where the upper story has all of the walls and all of the stiffness, and the lower story is a real open structure. What I mean, people use underneath for parking and different things. Probably may put the laundry downstairs as well. But it's an open structure. As engineers, we think that this is very dangerous because this is something called a soft story situation. What does that mean? It means that the upper story is 70% at least as stiff than the lower story from the lateral stiffness. Remember we talked about lateral stability, shear walls and bracing does it for us. The upper story is 70% stiffer in the lateral direction than the lower story. So in Turkey earthquake that happened a few years ago, the primary mode of failure was soft story. Why? Because you have a building whereby the upper floors are being used as offices or residences. They're enclosed. And a lot of the lower stories are used as shop front because that's where the shopping is. So there's a lot of glazing and glass, and you have very open structure down below. And upstairs you have the walls separating the rooms for the offices or residences or whatever. Soft story collapse is very dramatic. In Tobago earthquake in the early 90s, this would have happened as well. And if I start to shake this, get ready for bouncing balls and stuff. But what would happen is that what should happen, and don't embarrass me, please. Do not embarrass me. If I shake this, because this is so stiff and rigid, this should pancake down on the lower story. So let me just compare that to. So one may ask the question, where would an engineer help me with this? You know, we don't have to do actual calculations, and we could advise, look, stick to what is best practice. You don't have to enclose the whole thing, but put in some walls adjacent to the columns, the same 10 feet wide or 8 or 7 feet wide, so that at least not all of it is open. Have a series of walls around the columns, so that it stiffens the structure down below, so that below does not feel as flexible, as wobbly as in this situation.
Right.
All right? So you have that case. So that's all part of structural behavior. This demonstrates it properly. This shows you why a warehouse building is stiff, and how these cables, by the way, are in they're tension only. What does tension mean? It means it's being stretched. So it cannot, if wind came from this direction, this member will buckle, but this one engages.
Correct.
When it reverses, this one buckles, but then this one engages. So therefore, it's laterally stable in all directions. Okay? Now, sometimes a client may not want cross bracing. A client may want an open field, like what we saw below. That's where we come in. We will size the columns and the beams and the joints to be strong enough to take the loads from the lateral and the gravity.
So what you're saying, there's a solution
for
this situation.
Yes. And they said the solution really is to enclose, build some walls, you don't have to build a full wall along a full elevation. Build walls around the columns so that you get that stiffness in the lateral direction for the lower story as well.
Okay. So if there's like, let's say for instance, there's a column every 10 feet,
Right.
you're saying fill in one of those gaps on each elevation of the property.
Yeah, a column every 10 feet. It may end up being probably for 40-foot building, probably you get 4 or 5 columns or so.
Yeah.
We This the engineer now. We can say, you know what, we can, since there's so many columns, we can use these columns and beams to form a very strong frame.
Okay.
Or, as you correctly said, focus on the 2 corners in the end base. So
Right.
the last 2 columns, you place a wall between those only. The middle columns remain clear.
Okay.
Right? So that in itself will help tremendously in preventing that sort of failure.
That was a bit disturbing, I must admit.
Yeah.
Because I've seen a lot of, and it sounds bad, but I've seen a lot of residential houses built that way.
Yes. They're either designed that way from the outset, or as I said, a lot of it happens to where a client wants to do phase 1 and phase 2, and the lending institution is saying to you, we prefer that you do the upper story. Because once that is done, we know that the roof or the final project is finished as well. All right?
Yeah. Okay. And let's see, you have a third model.
I have a third model, and I have another model. Podcast, I have to get something.
Go ahead.
Let me go to my MacGyver bag. just give me a quick moment.
I see you have a third model. Can you just tell us what this one represents? Or
Yeah. So again, this is just a portion of a house. Let's say that I had a homeowner who wanted to have, opening onto the pool with the terrace.
okay.
All right? And we had someone that did not engage the services of an engineer. So they built this and they said, oh, when I built Miss Marshall's house, I used a beam that was, 300 millimeters deep by 200 millimeters wide.
Mm-hmm.
Yeah, I've not gotten so when I load it up, you can see the deflection. So
Right.
see the deflection. The deflection is how much that beam droops, for lack of to keep it layman. So if we put a load on this, all right, you'll see how it droops, okay? We call that deflection. Now, if I had to say, or let's say an architect had done a design for another client who said, you know what? I want indoor-outdoor living. I want to be able to look from inside my entire living room space and look right back onto the pool and pool deck. And I want larger spans. I don't want a little small door, 2-3 foot wide doors, side by side, 6 feet, 1.8 meters. I don't want that. I prefer to have a longer span.
I can see where this is going.
If I load this up, see how flexible it is, and picture you have glazing or glass beneath this opening. And the person that built the one before used a 300 deep by 200 wide beam and said, I can use this exact same beam. And then the owner moves in, and the first time that they look at the glass, they see a crack in the glass, and they're wondering why, and it's because the beam used was too shallow. So as engineers, when we know the span of something, we can calculate the depth of the beam. If it's a reinforced concrete beam, how much reinforcement has to go into that beam. If it's a structural steel beam, you'll watch HGTV, they will say, oh, bring in the steel girder.
Right.
That is a steel
correct.
beam, has a shape of an eye. We would be able to determine from calculations how deep or how thick, how wide that beam has to be, so that the deflections are within acceptable limits that we are prescribed by standards for sensitive material below, so it doesn't crack. So I just wanted to demonstrate how same load, check the deflection. Much more deflection.
Okay.
Yes.
So I see that and I understand that. Pretend I am the unknowledgeable homeowner who's gone to the architect or whoever, and the contractor said, we can do that. How do I resolve that issue? Because if we build that, you coming in after, how do we resolve that? You may tell me come and put something there, but I don't want that. How do I fix this issue or challenge?
Yeah. So if you don't want the column, which is the easiest solution, you have 2 scenarios, or you have a scenario which can solve it, but then it all depends in principle as to where you are in your construction or in your procurement. If the homeowner has already procured the glass doors, the solution that we would offer is that we may say, listen, we are ignoring this beam. We're going to put a steel beam, design a steel beam.
Right.
Let's say that's for reinforced concrete. We're going to design a steel beam that can now span from column to column.
Okay.
And that steel beam then, so we're ignoring this.
Right. Okay.
But what happens is that if the homeowner has already purchased the doors, then they'd have to obviously probably tell them that the doors can't work because now the height is reduced.
Correct.
So it's a case where you would have to, say about the door then is in the case now of who pays for that. Who pays for the reordering, who pays to make it right? Right? And that's where contractual situations arise in construction. In fact, I tell a lot of clients and people, students, engineering is the easy part. The hard part is the people and the contracts and the agreements and the disagreements and who's responsible for what, and did this person follow the drawing correctly? Did this person follow the instruction correctly? That is where the hard part is. And I think in most businesses you have a situation where your day-to-day work is not the hard part. The hard part is dealing with the different personalities, and as an engineer, we work with so many different personalities. We work with architects, we work with mechanical, electrical, and plumbing engineers. We work with quantity surveyors, we work with the planners, we work with the homeowner, the client, and we work with the contractor, who has a team under them. So you can see where a lot of having contracts in place is very important, because a case like this would probably result in somebody being sued or something like that. But in terms of the engineering behind it, if the client does not want an intermediate prop or column, then they would have to. The solution would probably be having a steel beam, but now the headroom is now reduced. So then what happens now with the door, right? Another option would be if you're not, based on where you are in the construction, if they only have placed the beam but not the structure above in its entirety, some people may say demolish it and make it right.
That's fair.
Demolish it. I have ordered the doors. I'm not going to carry them back. Make it right. Again, it comes back to who pays for the demolition and who pays for the rebuild to make it right.
Okay. So
all right.
Here's my thing. You buy a piece of land, you get an architect to design a house. Typically, it's your dream house. You go to town planning, you get planning permission. The typical thing after that is to get contractors' quotes, go to the bank, get funding, start building. Are you suggesting that we should really consult an engineer before we even go to town planning or the bank?
Not in every case.
Okay.
I would tell you, OECS building guideline has caveats.
Okay.
Caveat number one, the structure must not be more than 2,000 square feet. This is for non-engineered buildings. Non-engineered meaning that they have a guideline with details.
Okay.
And these details are prescriptive. I mentioned this word already. So the 2018 guideline document states, houses, single story, less than 2,000 square feet. No engineering input required. Conventional shape, rectangular shape, because shape also there are several factors and components that play a role in how stable a building is under gravity load and under the lateral forces that I mentioned earlier. Shape is one of them.
Yeah.
If you have a 2,000 square foot single story residence, and it's rectangular shape, conventional shape, you don't really need an engineer. And the guideline will say that, because there are standard details that you can use to build this. If, however, the architect has designed something, and this happens a lot now, where a lot of homeowners, more often than not, I would say they're looking for an open plan ground floor.
Correct.
And above would be the bedrooms and everything. So picture you have a concrete roof. So picture you have a concrete roof supported by walls on first floor, and there's no walls continue down to ground floor.
Yeah.
As engineers, this is a nightmare for us, because it requires either telling the architect, Madam or Mr. Architect, this requires some internal walls at ground level, and they will catch a fit and say, no, the client has already agreed, we want open plan. And it required the engineer now to start looking at what we call transfer structures. A transfer structure is what it says it is. It transfers the load from one level to try to get the load across to the surrounding perimeter supports.
Right.
All right? In a case like that, I would definitely say, what the architect would say, we need an engineer. Because they understand that the slab that we are using may not be sufficient enough to take the loads from the concrete roof and the walls for the bedrooms above. So they're the ones to say, look, client, I think we should get an engineer. Some clients are very, and as I said earlier, a lot of clients are like this. They want to protect the investment, and they say, listen, I just want an engineer. Even though it's 2,000 square feet, I want an engineer to make sure that my foundations are right, that my walls are detailed correctly, that my roof is detailed correctly. And that brings me on to a point, where so often, I always tell homeowners this when I interact with them, right? If you deal with a contractor, and I would say even, and I'm not knocking contractors, so even if it sounds that way, I'm not doing this. I'm just saying from my experience, and this has happened to me where I would have interacted with a client in the presence of a contractor, and their comment would be, I have been building for years and nothing ever happened. I get very scared. Because as I say, we have not experienced anything. We have not experienced, the 2007 tremor was a tremor.
Yeah.
It was nothing. Thomas 2010, Elsa 2021, Beryl last year. Nothing.
Yeah.
Yeah, nothing. And this is a case in point example that I have here again, where this detail, picture that this is a timber rafter. For those who don't know what timber rafter is, it is a roof framing that supports your sheeting over your head. The timber framing that supports the sheeting above your head, yeah. So this is a detail that coincidentally was in the Barbados 1993 edition. But
Really?
after Hurricane Hugo in 1995, and that's another thing too, as engineers, we learn from failure.
Correct.
So when something fails, we investigate what was the failure, what was the cause, how did it fail, what was the mode of failure, and from that we then enhance codes or standards. In fact, in California, they update their codes every 3 years, so the current code is always outdated. Because every 3 years they look to update it, right? So I have a situation where this could be a rafter coming down on an edge beam or a ring beam, roof ring beam. And what a lot of contractors may still do, or people may still do, we say people, just to make it open-ended. They may place a hole in the rafter.
I hope not.
So that, and then they will have a piece of steel that wraps around it. And they say, well, look, I have this piece of steel that goes through this thing here, and it's keeping it down, Well, what this big hole does, remember that when the hurricane comes along the eaves of the house, there's uplift forces. Mm-hmm. So it's uplift. So this is trying to keep it down, and the wind is pulling on this section here, pulling on the rafter. And if I had to pull on this, and don't embarrass me, please. I beg you, paper feel. And I have hurricane force winds. You see how it tears along where the circle is?
Yeah.
You feel your plane. Because the circle creates an area of weakness where as the stresses travel up, they jumble around the circle, and then you get increased stress. And therefore, that is why this detail was condemned, because this failure mode was witnessed a lot in after Hurricane Hugo 1995.
So let me ask you a question. I've seen that design in rafters. I've heard people say you don't place the steel hole, so to speak, close to the top of the rafter. You place it closer to either the bottom or the middle, because they obviously think the shear is going to be less at that point.
Yeah. So what I'll say to you is that this detail is condemned, by the way. Right. Let's get out of the way. Mm-hmm. If someone had to use it, the best situation where it may not fail for every instance of a high wind is if it's more in the middle. Why?
Okay.
Timber has requirements called edge and end distances requirements. Mm-hmm. If you place a bolt or a screw within a certain distance from the edge, then it will split.
Right.
And therefore, standards and international codes say, look, for example, for edge distance where the force is going towards the edge is 7 times the bolt diameter. Mm-hmm. So if we use a 12 millimeter bar, the 7/12 is 84. Mm-hmm. So you should be at least 84 mil away from the edge. Okay? We have to ask ourselves the question. When people install these things, are they aware of this? Are they aware that you should place the thing in the middle? Sometimes the bar is bending and weaving and wobbling.
Correct.
And wherever it gets to the point, they may drill another hole because it was at that point. So if you're too close to the edge at the bottom or too close to the edge at the top, depending on the loading direction, then it could be detrimental. So a safer bet is to be as far away from the edge or end as possible. Middle.
Fair.
Okay?
Yeah.
Now, the detail that engineers that we would prefer, same rafter, but this is called a BRC truss anchor. And this is sold off the shelf at any other hardware, local hardware stores, right? Where, as you can see now, it's less damaging to the timber because they're now using screws or nails to drill into the rafter.
Is it preference screws or is it nails, or does it matter?
It is almost like a debate where, the testing from BRC was done using nails,
Okay.
right? Some screws could fail very suddenly when they're in a brittle failure. So it all depends on the type of that you use. So I wouldn't necessarily specify and say screws better than nails better. It all depends on, the metallurgy of the screw. If it's too much carbon, it could be brittle. But the testing that BRC would have done to give the load tables would have been done using nails, right? And if you look at this, you can see the holes are less damaging. And if I try to pull it apart,
It's very difficult.
it's difficult. So this is a typical, this truss anchor would anchor into the ring beam, and this would wrap over the rafter and be nailed into the rafter's sides. So as you can see, it's less damaging to the actual rafter because you're dealing with smaller holes now. Okay? Yeah.
What are the challenges that you see today in construction, new construction, and, well, purchasing a house and, let's say, renovating it? What are the challenges you see at the moment?
Yeah. Let me start with purchasing a house first because, you mentioned challenges, but I think I should also mention benefits as well.
Okay.
I said benefit of purchasing a house obviously is that, sometimes not every person is visual. If an architect does a drawing, you could show a drawing to a client and all they're seeing is lines and words. They don't feel the space.
Correct.
If you're buying a property, you can walk into the property, you can visualize areas where you can take out a wall or renovate or extend or expand. You see it, it's there. So that's one benefit you would get in buying a property. Definitely, in terms of, I mentioned, right, if you had to do an extension as well, you can see what you're working with, right? And the challenge with buying a new property, obviously, is the year it was built. I mean, if it's built in the 70s, looking at a situation where, what was the form of construction? What was the quality of construction? What was the quality of materials? If you're testing materials, if you're testing concrete, is the concrete of structural strength that we, as engineers, would say is structural concrete of a certain strength? Was it reinforced?
Right.
Right? Are the blocks 4 inches, which are already partition walls? Some people have built load-bearing walls using 4-inch or 100 mil walls.
I'm sorry, I should not laugh.
Right? And, so those things come into play. Obviously, foundations. You can't see the foundations because when someone goes to buy a house, more often not when the engineer comes, it's really non-destructive testing. I can't come to, if you're selling a property, Brian, and someone brought me to look at your property, I can't come chiseling away at your house. I can't go and bring an excavator and hammer up your walkway around the house and look and see what the foundation's like. I can't do that. So I have to use engineering judgment. I have to use telltale patterns of cracks to make an assessment and say, look, good buy, bad buy. Okay? In terms of new construction, obviously, you get where in terms of quality of construction, you can dictate now, the performance criteria. I want my house to withstand a Category 4 hurricane. I want my house to be able to expandable. So allow me to have this. I want my house to be resilient. I want to recover as quickly as soon as possible after the passage of a major event, right? So with new construction, that's the advantage. The challenges would be, I would say, uncertainty too, as well as rates of foundations. That you may buy a plot of land, and you may not find anything of substance to build upon. That could be a risk. You may buy a plot of land to build a house, and you may not have engaged the services of an engineer or qualified architect. You could have bought the land in a catchment area where flooding is an issue. You could get with a builder who starts out well, and then you may not see them anymore. That I mention it because this is a real life thing that's happening now. People are building houses, and they start, and then the next thing 2 months down the line, they can't find the person building the house. All right? And obviously people pay a bridging loan, and these things go on, and where does it end? An understanding process. If you drive around Barbados, sometimes you will see a lot of houses that start and stop.
Correct.
Sometimes if you look at them, there could be a common trend where someone may have excavated deep enough to get a basement. They start putting in structure for basement, and the lender is saying to you, hold on, we didn't give you money to do a basement.
Right.
We gave you money to do a floor above and finish that out of your own pocket.
Correct.
To get back to the ground level before we could give you money again. And they can't. All right? So I would say that those would be the challenges that come to mind for building new. But obviously, advantage will be you can specify the strength of your materials, the strength of your block. You can order concrete from the supplier and say, listen, I want 3750 at 28. Let's break it down. 37 PSI, 3750 PSI, which is the crushing strength for the concrete. Right? In metric, that would be 25 newtons per millimeter squared. But that is a performance spec that you're given for the house. I want all of my concrete to be of a certain strength. So when you have that, you get more control as to what you get in terms of quality.
Okay.
Yeah.
Over the years, we've seen. So we used to come with chattel houses before.
Right.
We've had coral stone houses.
Yeah.
More modern houses are concrete, precast concrete.
Yeah.
And now you're seeing some steel. I know there are challenges with everything, and there are also advantages with everything. Steel is not as common as concrete, and wood is not as common as concrete anymore either. Do you see steel as the future for building houses? I know it's a more European kind of building technique. Mm-hmm. Do you see it as a viable option here, given that concrete costs have gone up, building costs have gone up, and people are looking, to save some money somewhere? Do you see steel as probably the next option?
Yeah. I would say that it is a viable alternative, but it comes back to what you just said. You just made a very good point. If a structure is properly designed, if it's properly built, if it's properly constructed, if it's properly maintained, then you shouldn't have any major issues. The design part of it deals with the quality materials as well, because you don't just want to say using steel without specifying a finish to steel. We are in a marine environment. If you live in St. George and St. Thomas, you're in a marine environment.
Very much so.
Parts of the UK, if you're in close to the coast and it's even further away from the coast, from St. George and St. Thomas is from our coast, they say that they're in a coastal environment. What does the coastal environment do? It will bring harsh conditions that could cause the steel to corrode. And therefore, the finish of the steel is very important. Aluminum is a very good product, but it's expensive. Galvanizing steel is good, but the issue you have with galvanizing the steel is that when it gets to site and is manhandled, if that galvanized layer is scratched, then it causes a localized area that could be that can corrode in the future. So obviously, steel is a viable alternative. In fact, what you're talking about probably is what we call light gauge steel.
That's correct. Light
gauge steel or cold form steel, as we would say as engineers. That really and truly is the competitor to conventional timber houses. It's the same principle. You have metal studs, timber studs. You have headers and wall plate, wood wall plate, wood header, same thing. And you have it clad with either drywall or concrete board or something, So that is really the replacement for timber. Why would people gravitate towards it? Timber could get, wet rot, dry rot, termite infestation. The steel, the main thing with the steel would be corrosion. Right? So yes, it is a viable alternative in terms of the light gauge steel houses that you're seeing. And again, it all comes back to being properly designed, built, constructed, and maintained. Because if all four of those things are not there, you have a situation where it's properly designed, but not properly built. In other words, people missing screws between the connections, not properly maintained. In other words, the person sees rust on the surface and just leaves it there, and corrosion continues to happen without treatment, localized treatment. That's where the maintenance comes in. So, answer your question, yes, there's a space for light gauge steel housing.
Okay. Designing houses or structures generally, and we're separated into commercial versus residential. What level or minimum hurricane force or category should a house be designed for now, today?
Yeah, so what I would say for this one, right, are two things. I can approach it from two perspectives. We are lucky enough that in 2018, there was a study done by Vickery, who is a world-renowned wind. He does a lot of testing of wind tunnel testing. And after Irma and Maria in 2017, he would have done new wind speed testing and testing studies on the Caribbean basin, the Caribbean belt. And he would have come up with a series of contours for each island. And he would have also have a series of return periods. This is the mathematical part. I'm just going to break it down to you. An event that is rare and huge has a very large return period compared to an event that happens every day. There's a short return period. Similarly, you have to think about the use of the building, the risk category of the building. If it's a hospital compared to if it's just, some little animal shed. You can't get the same level of wind speed to those types of things. So therefore, that's where return period also comes in, So we have standards that dictate what wind speeds we should use for Barbados given the risk category of the structure. That's specified for us. We could just use that directly. We could tell the client, look, this is what we are following standard. This is what you would be getting.
Okay.
Those standards also we have a climate change factor included. So as engineers, we put factors of safety on things because, give a good example, you could be a principal of a school and you get this new school. The engineer could have designed the walls as load-bearing walls. 50 years from now, another principal comes and say, let's knock out all of these walls to make an open space below. So therefore, it comes back to the same hurricane thing where at the end of the day, how the building is used affects the design category of speed that we would select from the charts that we have. But they also have a situation where a lending institution can dictate the performance.
Really?
Yeah, so if you may have, I don't want to call any, but you could say some lending, for major projects, commercial projects can say, we want resilient design, we want this to be designed for category 5 lower end because category 5 is open-ended.
Yeah.
Lower bound category 5. And that's what they can say. And then the engineer then would just use the wind speed for category 5 with the appropriate factors and then apply those pressures to the structure and then start doing the calculations. So I would say that there's no right or wrong answer for this. I mean, obviously storms are getting, based on 2017, 2018 with Dorian as well, that's to days over the Baco Islands, right? I would say that storms are getting bigger. And if there's a case where people say, well, storms are always big, they have category 5s and 4s in the day, the potential for it to happen could be, the probability is more so now than before because, formation of a hurricane is based on the temperatures. Maintaining 26 degrees over a certain period of time then develops into a storm and then a hurricane. And if you have temperature rise, then you can see why you would get more frequent storms.
Correct.
And probably more frequent, bigger storms, right? So that's why I would say, if it were me, I would tell the client, look, category 5 lower bound, which is 155 miles per hour, and go from there. The idea that you may say, oh, that's going to be so expensive. Not really. If you go into a hardware store and look for the price of a hurricane strap, which is, I'm saying hurricane strap. They all have, strap is the general name, but what I showed you before with this one is a truss anchor. So this is a special use. There are things called rafter to purling clips. Yeah. There are things called rafter to ridge connections. These things cost less than $4 off the shelf. What people are doing now, you will see a lot of modern construction using concrete roofs. A concrete roof can't blow off. Remember, so how it goes is that hurricanes and earthquakes, they like different people. Picture that there are people but they just don't have different legs. Hurricane like to offset lightweight structures. If you lightweight, hurricane coming for you.
Yeah.
If you lightweight, because I have to do this. Back in secondary school, we learned that force equals mass times acceleration. Yeah. So the force is proportional to the mass. So the heavier something is, the more force it attracts. So if the seismic shakings from the ground, a heavy structure attracts a greater force. Lightweight structure, no. Hurricanes don't like heavy people. I can't get you budge. I push it, he ain't moving, she ain't moving. Hurricane can't handle a heavy roof. I try to lift it off, I can't get lift off. Hurricane loves a lightweight roof.
Yeah.
So a lot of people now are building structures with concrete roofs. Homes especially, a lot of residences are using concrete roofs. And I think that in terms of category 5, the roof ain't going away. I know a category 5 cannot blow off a concrete roof. The downward weight is much greater than the upward force from the hurricane. All right? You may get stripping of the waterproofing. That can happen. Happened in Antigua in Irma, where the torch-on membrane, if you're using torch-on, peeled away. But the roof ain't going nowhere. All right? So it can happen, and because people are inherently using the concrete roof, and the cost between the concrete roof and the timber roof is right now very, very competitive.
Yeah. Yeah.
You know? People may argue and say, some people may say, concrete roof, that means the house can be hot. If you vent it properly, no. And the thing that they may not think about is that if you are going to exact same size structures in hot, boiling sun daytime, the timber structure will feel hotter and the concrete roof will feel cooler because of something called thermal massing. The more mass you have, the harder it is for it to heat up the space. The issue comes where at nighttime, the timber has already vented and gotten rid of all the heat that it had absorbed. The concrete roof is now saying, let me release this heat. So that's where venting becomes important. But you don't hear people complaining too much about the heat for a concrete roof. I haven't. I mean, if they have, that would be the reason why. Because at nighttime is when it's venting or releasing this heat energy that it had gained throughout the day.
Okay. On a lighter note, what is your favorite project that you've worked on or been involved in? And why? Doesn't have to be local, it can be regional as well. Or international, depending on where you are.
Yeah. I would have to say, for me, from that moment where I felt the role of an engineer more than ever, and I have to thank the architect for that. At the time, it was an architect, Bruce Jardine from Gillespie and Steel. What would have happened back then is we wanted a new medical faculty here in K-Phil.
Right.
And the requirement was, because every project has a brief. What is the brief? What does this client really want? The client would have given the brief to the architect, and the brief was, we want 50-foot clear spans. We want a lecture theater. And when I first started to work, when one studies engineering and they start to work, you have to work for 4 years under a registered engineer before you become a registered engineer or registrable. And I recall that when I first started to work, you were seeing real projects being built. And for me, when I met with him and he said, you're the engineer, tell me what you can do for me to get 50-foot clear spans and consider you have medical equipment. So you have to think about vibrations and sensitivity to equipment, that sort of thing. I was able to, go back and look at it and come up with a structural scheme to achieve the clear spans that would have been needed at the time. So that felt good because it was almost like, you had a definitive role to play in dictating what structure is being used to make these spans be achievable. I would also say, I know you have to include, the airport at the time. We were resident engineers there. And what that means is that when you're a resident, it means that that's where you go to work. So you have a typical project where an engineer may just visit the site and do occasional site visits upon request. So you can say to me, Greg, the foundations are still in place. Come have a look and tell me if it's okay. I can look and say, yeah, good to go, pour. But then there's also a situation where the job is so important, so many moving parts, that I will begin called out every 2 minutes, get me desk and sit down. So no, you go to work there, and once the contract is ready for inspection, you are right there. So you can just get in, drive a couple minutes, and you are at the site to inspect. So that was a good view from the resident engineer perspective, where I wasn't going into the office, I was going in to work at the airport, right? I would say that those are the two meaningful for me because it touched different parts of how I felt about engineering. The first one being having to play a role in dictating how a structure could remain open in terms of open space. And the other one is obviously is a national project. It's one where it's so critical to tourism, new airport, aesthetics and everything coming into play. That for me, being a resident engineer and being a young engineer at the time too, and dealing with international contractors and international consultants, it really opened my eyes to see how professionalism really is supposed to be. How people are supposed to work together, how people are supposed to share information, And that is where, for me, I felt that being more professional in how I approach, deal with people and that sort of thing was a good eye-opener for me.
Sounds good.
Yeah.
You want to let our audience know how to reach you?
Yeah. So because, as engineers, we one thing I would say is that Barbados, we are blessed. We have a lot of very good engineers.
Okay.
And I would give you 2 contacts. Obviously, CEP's contact would be 426-5930. But we have an association called the Barbados Association of Professional Engineers. And we have a secretary out there that is, she's very helpful, Stacey Burgess. And you can reach them at 4296105. And I think she can, so if someone wanted to get access to an engineer, as I said, for interacting with others around the region and internationally, I think that our engineers here, we can hold our own, against the best. And that's why I would always be, someone who promotes the profession and promotes the talent that we have here on island. Yeah.
Okay. Mr. Greg Parris, thank you very much.
Pleasure.
Ladies and gentlemen, my name is Brian Puckerin. Thank you for joining this episode of Terra Talks.
Thank you.